Okay, so let's begin. So before the break, we discussed a lot about like what would be the optimal function for doing regression, and also how is k nearest neighbor or linear regression trying to approximate this optimal function, right? So now let's do a similar discussion, but for classification. Okay, so now as you remember, the difference between classification and regression is the fact that the output in classification is a categorical variable, right? So let's say G. Now this is a random variable, which is a discrete variable with a fixed set of options, okay? However, the same paradigm works here. Okay, but we need a different loss function for penalizing the prediction errors. Okay, so now let G, descriptor G, be the set of possible classes. If you have a 5-class problems, then you have like 1, 2, 3, 4, 5, right? Now G hat is the model's estimate. Okay, now we are going to define a new loss function specifically for classification. Okay, now this loss function is going to be a k cross k matrix. 1, 2, k, 1, 2, k. Okay, now every entry in this matrix, let's take this entry. This means what is the price paid for classifying an observation which is from class 1 to class k. So this is like the penalty or the loss that you're going to pay for misclassifying 1 as k. Okay, so now obviously if you classify 1 correctly as 1, you get 0 price or 0 loss, right? So the diagonal of this matrix is going to be all zeros. Now you could put any value that you want for the remaining entries of this matrix, right? Like so the most common loss function that people use is 0-1 loss function, which basically says you get 0 if your predictions are correct. If your predictions are wrong, for example, you predict 1 as class 2, class 1 as class 3, then you're going to get a loss of 1. Okay, so now this is basically a k cross k matrix, where k is the cardinality of the set G. So it's the total number of classes that we have. Okay, now we can formalize this loss function. So this we can write this as L of k comma L, which basically means the price for classifying an observation belonging to class K to class L. Fine. Okay, now we have a loss function. So now we can do the same procedure again, right? So what is the expected prediction error? So what is the expected prediction error? So now the expected prediction error is given by expectation over the loss function. G hat of X. G is the true class, G hat is the model's prediction. Okay, now this expectation is with respect to probability of G comma X. Remember that in the case of regression, the joint distribution comes from probability of X comma Y. In this case, the joint distribution comes from the input X and the output G. Okay, now also X is continuous. It could be discrete too, but let's say X is continuous, but G is discrete, right? So now the expectation is not by integrals, it's by summation. So this is going to be expectation over X, which is continuous. Let's just keep it as E of X. Summation over K is equal to 1 to K. The loss that you get, right? Probability of GK given X. Okay, so now what does this say? So the expected prediction error is given by expectation over X. Then you have expectation over gk given x. Now that expectation is given by this summation over all possible classes. So what is the loss in, okay, first of all, what is the probability that the class is gk? If the class is gk, what is the loss for this model, right? Again, it suffices to minimize this EPE point-wise. We don't need to worry about the expectation over x. So they're just going to remove it and say the g of x that we are interested in, right, is going to be R min. Okay, so I think I'm confusing you guys by different notations. Let's just call this g star since we are looking for the optimal function. So g star of x is given by R min over g belonging to g, summation over k is equal to 1 to k, the loss probability of gk given x is equal to x. Okay, so now for 0, 1 loss, now g of x, sorry, g star of x, right, is given by R min g belonging to g. Okay, so now in the case of 0, 1 loss, the loss is either 0 or 1. So you want to minimize the misclassifications, right? So the for every misclassification, you get a value of 1, right? And you have some probability associated with that. So that is given by 1 minus probability of g given x is equal to x. Now, if the correct class has probability 0.7, 1 minus 0.7 is the probability for the remaining classes, and they all have a loss of 1. So it's basically 0.3 times 1, right? So now I can also write this as g star of x is equal to, instead of arg min, we could do arg max and just reverse this probability of g given x is equal to x. Okay, so now this is the optimal decision function for classification if you are using 0, 1 loss. Now again, what does this function tell us? So this function tells us that the best possible classifier is a classifier which picks the most probable class given some x, right? So again, like, so the same issue. So like we cannot implement this. Okay, so I think I'm making the g hat mistake again. So we cannot implement this g star. Why? It is the same reason, like we don't have access to probability of g comma x, right? If we have access to this probability distribution function, then we can exactly compute this, right? So that particular classifier, the optimal classifier for classification, right? So it has a specific name, it's called Bayes classifier. Okay, so now whatever error that this particular classifier is going to have is known as the Bayes error rate. Okay, so this is an important term because Bayes error rate for any particular problem is the lowest possible error rate that one can get. Remember that this Bayes classifier has access to the true probability, the joint probability distribution over G and X, right? So if you have, even when you have access to the true probability distribution, since the problem itself is stochastic, you're going to get some error, and that error is the Bayes error rate. So this is the lowest possible error that any classifier can achieve. Okay, and as you can guess, often it is not possible to compute the Bayes error for the problem in hand, simply because we don't have access to the joint distribution. But for the toy example that we have been discussing in the lecture, I generated this data set. So I created the joint distribution, which is the probability of x1, x2, comma, the class, which is blue or orange, right? So I created this probability, I sampled this data from the probability distribution that I designed. So I can actually compute this particular function in a which is, so it's possible in this case because I have access to the true function. And this is how the Bayes optimal decision boundary will look like. So this is the optimal base decision boundary for the toy task. Okay, so now you can see that even this optimal decision boundary has errors. So you can see there are these orange points which are misclassified. There are these, okay, and there are these blue points which are misclassified, right? So now this is something that you cannot eliminate. So in some sense, this is the irreducible error. And it often comes from the stochasticity of the task or the problem itself. Okay. So now what have we learned? So we have learned that the best possible classifier that one could have for classification problem is this G star, right? Now let's ask the same question. So how is K nearest neighbor approximating this solution? So K nearest neighbor approximate this solution by using majority voting in the neighborhood, right? So instead of computing this, so what is K nearest neighbor doing? So it directly approximates the solution by doing majority voting in the neighborhood. Okay, so again, so the conditional probability at a point, right? This conditional probability is relaxed to conditional probability in the neighborhood, right? So this is approximated. Similarly, instead of taking argmax over, like instead of having this argmax, like, so we are going to have our probabilities estimated by the training sample, since we don't have access to the true distribution. Okay, so that is how K nearest neighbor is approximating this. Okay, so I think that concludes the first half of what we wanted to discuss today. So to summarize, like what we have learned is, given a problem, whether it is regression or classification, like what is the optimal function that one could achieve, and how are the two algorithms that we have learned so far in this course are approximating these optimal functions. So I will take a couple of questions here before we delve into the details of regression and possibly nonlinear regression. Any hand raises?
Don't see any questions so far.
Okay, so I hope I did not discourage you guys by saying that you should not ask questions in chat and you should do hand raise. So hand raise is mainly to make sure that you can ask your questions at the points where we are without interrupting class. Okay, so could you please okay, I'm sorry, the reference for the second half, I have posted it already. It should be in the schedule page. I know I wanted to do this at least a week before, I did it at the last minute. I will not do this for the next lecture. So the references are the notes for the current half is in the website already. But for now, you could just follow the lecture and then go back and look at the references. Okay, so maybe let's continue. So we are going to look at regression, but in more details. Okay, so specifically, we'll first start with linear models for regression. Okay, now this is a recap. Okay, so the simplest model that we have seen so far is linear regression. Right? In the case of linear regression, y hat of x given w is given by w0 plus w1 x1 plus wp xp, where you have p features in your data, right? Now this is specifically like this equation is a linear function of the parameters W, right? Like W is a vector which has all W0 to W2. Okay. Now there is a limitation. Like, well, the obvious limitation is this is just drawing a line, right? Now, the limitation here is this function is also a linear function of the input variables x1 to xp, right? So while this is a linear function of w, which we found to be a very useful thing, because when it is a linear function of w, we can derive closed form solutions easily, right, and implement the closed form solution. But it is also a linear function of the input, right? And we actually discussed this limitation even in the earlier lectures, and the solution that we came up with was basically making it more richer by considering polynomials, like degrees of x instead of just the linear x, right? Now we can actually generalize that idea into what is known as the linear basis function models. Okay, so the idea of linear basis function model is we are going to have this new model, which is W0 plus summation over j is equal to 1 to m minus 1 wj phi j of x. Okay, so now I'm going to consider m minus 1 functions phi j, which are known as basis functions. Okay, these are typically a fixed non-linear function. Okay, so like the best example that we have seen is like polynomials, right? So for example, the first phi could be x squared, the second phi could be x cubed, the third phi could be x power 4, and so on, right? So now this is a hack that we are doing here. So we are essentially taking a linear model, which is both linear in terms of parameters and the inputs. And our goal is to come up with a model which has non-linear decision boundary, right? So we want something which has complex decision boundary. So there are two ways in which you could do this. Either you make the model non-linear with respect to W, which is something that we cannot do right now because like we have only learned how to do closed form solutions, right? Like so if you, the moment you make the model non-linear with respect to W, you cannot come up with a closed form solution. Or a cheaper thing to do is to make the model non-linear with respect to the input. So we can do that by taking the input and adding a non-linear, fixed non-linear function to that. Okay, so now I can actually use the same bias trick that we did before, like where you put W0 inside the summation so that you can have like a vector notation. So I'm going to write this as summation over j is equal to 0 to m minus 1 wj phi j of x, okay, where phi 0 of x is given by 1. I just add a 1 to the input so that 1 times w0 goes inside the summation, okay? So now this thing can be written as w transpose phi of x, okay, where w is given by w0 to wm minus 1. This is the parameter vector, okay? This is my parameter vector. And then we have phi, which is phi 0 to phi m minus 1. Okay, so this is my input vector. So what we have done is we took the input, which was x1 to xp, p-dimensional input, and we did some transformation phi, which gave us phi 0 to phi. Let's also put x0 here. Okay, so now this function is a nonlinear function of x, right? So this one. So let's put this as y hat of x given w, right? So now if you look at this function is a nonlinear function with respect to x because of the phi or phi. Nonlinear with respect to x. But remember that this is still linear with respect to W. Or in other words, we could still find the closed form solution for even this nonlinear decision boundary models. Okay, so we will still call them as linear models because they are linear with respect to W. Okay, so now let's look at some examples of basis functions. Okay, so the first basis function which we have already covered in this course is polynomial basis function, right? So in the case of polynomial basis function, phi j of x is given by simply xj. Okay, now there are many other basis functions that one could use. So we will see a couple of examples. So the second basis function that we are going to see is Gaussian basis function. Okay, which is given by phi j of x is equal to exponential of minus x minus mu j the whole square by 2s square. Okay, in this case, mu j basically governs the locations of the basis function in input space. Okay, and S governs the spatial scale. Okay, so a quick note here. So this is not the actual Gaussian distribution. Okay, so now this looks like a Gaussian. That's why we are going to call this as Gaussian basis function. Mu j is not the mean. S is not variance or standard deviation. Okay, so now these are just hyperparameters. So now the mu j and S are hyperparameters. We are not going to learn them. So these are hyperparameters of Gaussian basis function regression model. So we will pick some m minus 1 mu j's and sj and s, and we are going to use that to transform the x to something like a Gaussian. Okay, so this Gaussian basis function has no probabilistic interpretation. So this is not the Gaussian probability distribution. Okay, and also the term S is not a normalization constant. Remember that there's no need for a normalization constant here, because in the end we are going to multiply this phi with a W. So we are anyway making it a bigger number or a smaller number by using the W, right? Okay, so now let's look at one more function, and then we will see like how all these basis functions would look like. So the second, like, maybe let's look at how the first two functions will look like. So polynomial is given here, right? So this is polynomial of degree 1, or the identical function, and then like you have various degree polynomials here. So similarly, the different Gaussian basis functions are here. Like so you could see that this function is centered around 0.1, this function is centered around 0.2, and then it has a specific bit and so on, right? So now when you combine a bunch of these Gaussians, you're going to get a really complex decision boundary. Okay, it would be a fun exercise for you to go and try to implement like a bunch of these basis functions and see how their combinations look like. Okay, so now we will also look at one more basis function, which is sigmoidal basis function. Okay, so the sigmoidal basis function is given by sigma of x minus mu j by s. Mu j and s are again hyperparameters. Okay, the sigma of a is given by 1 by 1 plus e power minus a. So this is known as the logistic sigmoid function. Okay, so now this is how the sigmoidal function will look like. So you have a bunch of sigmoidal function here, like each centered around different mu j's, and you could combine a bunch of these to come up with a nonlinear model, nonlinear decision boundary, not a linear. So there's a difference between a model having a nonlinear decision boundary and the model itself being nonlinear. Okay, so finally, like when we use something like identity function, then we would recover the normal linear regression. So phi of x is equal to s. Okay. Okay. So now we looked at a bunch of basis functions, and we have also come up with this new generalization of what we earlier discussed in the name of polynomial regression. So we are going to call all these types of basis functions based regressions as basis function regression models. Okay. Now we could do the same least squares even for this model. The residual sum of square error is given by y minus phi w transpose y minus phi w. So instead of having x, we have phi. That is the only difference, right? So in this case, w star is given by r min of w, rss of w, right? So now the solution is exactly the same. It's going to be phi transpose phi inverse phi transpose y. Remember, when you had x, it was x transpose x inverse x transpose y. Now we just have some transformation, so the solution is going to be very similar. So there is a question which is, are the basis functions considered as hyperparameters themselves? It's a very good question. So now how do I choose which basis function to use, right? So given a data, how do I know whether using Gaussian basis? There are a lot of questions here, the same questions here. So the first question is, how do I choose which basis function to use? Then the immediate question is like, if that basis function has hyperparameters, how do I choose those hyperparameters, right? So now these are some questions which does not have obvious answers. So these are questions like where we don't have the right answer. So these are hyperparameters, and we often have to do model selection by trying different different basis functions for different hyperparameters of the basis functions and pick the best out of the validation set. Okay, so now this particular term here, right, it has a special name. So this is known as Moore-Penrose pseudo-inverse of matrix phi. Okay, so we will just call this as phi plus. Okay, phi plus is given by phi transpose phi inverse phi transpose. Okay, so a quick note. If phi is square matrix and invertible, in that case, this becomes the exact inverse instead of pseudo inverse. So phi plus becomes phi inverse. Okay. Okay. So now, what have we seen so far? Like, so we started with simple linear regression. So then we said, oh, okay. So for now, we want the model to be linear with respect to the parameters, but there is no constraint on the model to be linear with respect to the input x. So we can actually come up with nonlinear basis functions, which could make the model nonlinear with respect to x, and hence can help us to come up with complex decision boundaries, right? And we saw a bunch of examples, and we also saw that least squares, in fact, can be easily extended to this situation. Okay, so maybe I can take a question here. Lawrence, can you unmute Masood?
Sorry, just a question. This substituting a linear regression with some nonlinear functions. I mean, what's the purpose of this substituting? Still, this combination of functions still is a function, and we cannot predict something already k-nearest neighborhood is doing. I mean, have a circle boundary or something like that.
Well, that is true, but well, like it's kind of like a good observation that like whatever polynomials we are going to do, maybe we cannot reach the k-nearest neighbors, right? Like, but remember that like in the whole point about the curse of dimensionality is k-nearest neighbors is not useful when you are in higher dimensions, right? Like then you are dependent on some model-based algorithms which has these functions where you're estimating the parameters. So well, of course, like which is the right algorithm to use for which task, that itself is a hyperparameter, right? Like sometimes you need to try a bunch of algorithms and
okay,
see
so
which.
Maybe I should ask the question in another way. I mean, the whole purpose of doing this is just a two classifier. I mean, building a classifier.
In this case, regression model.
For now.
Regression model.
Regression model for two classification prediction.
Yes.
Okay, perfect.
No, this is not two-class classification. We are working with regression now. So there are no classes.
But non-linear regression.
In this case, it becomes a nonlinear regression. Yes.
Oh, okay, nice. Thank you. Yeah, that's
Okay. Okay. So let's continue. So now, like, I would like to give some geometrical intuition of what least squares is doing. Okay. So geometry of least squares. Okay. To do this, we are going to consider an n-dimensional space where n is the number of examples that we have. Okay. Consider an n-dimensional space whose axes are given by yn. Okay, so that the target vector for all the n examples that we have, right, is actually a vector in this space. Okay, so now let's do it with a simple example. So let's say I have 3 examples in my data set. This is just for the ease of visualization. Let's say we have 3 examples and we have 2 features. Okay, so when I have 3 examples, I will be in a 3-dimensional space, right? So let's say this is my 3-dimensional space, 1, 2, 3, the number of examples, right? So now for every example, I have my prediction that like there's a true y, right? So you put all those y together, y1, y2, y3 as a vector. Now this vector lies in this space. So let's say this is the vector y. Okay. So now we have 2 features, right? So let's call those features as phi1 and phi2. Okay. Now when you apply phi1 for all the 3 examples, you're going to get a vector of size 3, right? So let's look at the phi matrix. So you're going to have the data matrix is going to be, you have 1, 2, 3 examples. You have phi1 for that, phi2 for that, right? So this is the first example, second example, third example. Now consider this column, which is the feature column phi1. Now this phi1 is also lying in the same 3-dimensional world, right? So let's say this is phi1. Similarly, let's say this is phi2. Okay. Now we have lesser number of features than the number of examples. We have 2 features when there are 3 examples. So these 2 features, like remember that your linear regression is basically W1 times phi1 plus W2 times phi2, right? So basically, these features are going to help you to cover a linear like subspace of dimensionality 2, right? So now let's consider that subspace to be something like this. Okay, so now this is the 2D space covered by phi1 and phi2. Okay, so like we are interested in finding some prediction y hat which is as close as possible to this true y, right? So now how would that work? So the closest possible y hat that one could get in this possible set of y hats, right? Like, so for example, I'm going to use a different color. So this could be one possible y hat, 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 and so on, right? So now which is the closest possible y hat to this y? So it is basically the orthogonal projection of this, right? Like, so now basically you project this. Okay, maybe my pictures are bad, but like you project this and you get a y hat here. Is that clear? So in some sense, the least square solution corresponds to the orthogonal projection of y onto this subspace? Yes. So this is like the geometric view of what least square is trying to do. So what is least square? What is least square trying to do? Like, so like you have a bunch of features. Now these features form a subspace. Now your your regression model can only be a vector in this subspace because it's a linear combination of these features, right? Now we are interested in finding that y hat, which is as close as possible to y. And in this case, it happens to be the orthogonal projection of y to this linear subspace. Is there any questions about this viewpoint? Okay, Hossein.
Can you hear me?
Yeah.
Okay. So before, when we're talking about dimensionality, weren't we talking about the number of features?
Yes. Well, that is true. Like, but in this case, like in this case, for this particular, you could come up with interpretations both in different dimensions, right? Like, so in this case, the dimensions are the number of examples, and the features are like we assume that we have lesser number of features than the number of examples. So these actually lie within the subspace of this bigger dimensionality space.
Okay, thank you.
Okay, so there are actually.
I think before you continue, someone in the chat said, sorry, could you please explain this part a little bit more?
Okay, so yeah, so this is probably, okay, probably I did, like this requires a bit more time. Okay, so we are trying to understand what is linear regression trying to do. Okay, so linear regression, and we are going to consider this by using this specific example, which is, I have 3 examples. Okay, there are 3 examples in the data set, and there are 2 features. Okay, now when you have 2 features, Phi1 and Phi2, the linear regression model is given by W1 times Phi1 plus W2 times Phi2, right? So now consider a 3D space. Okay, this is my 3D space. Now, the prediction for every example is given by Y1, Y2, Y3, right? So my prediction vector lies in this 3D space, right? So now this is the target vector. Okay, in some sense, we want to find this target vector, right? Like we want a function which given x will map to this target vector, right? But how are we trying to do that? We are trying to do that by just using Phi1 and Phi2. And this picture basically explains that with Phi1 and Phi2, which are only 2 dimensions, like 2 vectors, you can only cover a plane, right? Like it's a 2D subspace of this 3D space. So now from this picture, you can see that you clearly cannot get 0 error, because to get the 0 error, you need to reach this y vector, and this y vector is not within this subspace, right? So if you cannot achieve 0 error, then the next question is, what is the minimum possible error that one could achieve? And the basic geometry tells us here that, so it becomes a geometry question. So now what is the vector in this 2D space which lies as close as possible to this vector y? And that is given by the orthogonal projection of y to this 2D space. Is that clear? Okay, thank you. Okay, so before we conclude, like there are a couple of issues with the model, like the linear regression model that we have discussed so far. I'm sure some of you raised these issues in the previous lectures, and I told you that I will cover it later, right? So the first issue is, if the columns of X are not linearly independent. okay, then X is not of full rank. Right? So if the columns of X are not linearly independent, then X is not a full rank, which means that X transpose X is singular. And hence W star is not uniquely defined. To give you an example, for example, let's say I have the second feature, which is exactly 3 times the first feature. Okay, now these are perfectly correlated, right? So now the rank is reduced by 1. So when you have like not a full rank matrix, then X transpose X is singular and W star is not uniquely defined. How would we solve this problem? Now I can take solutions. So like any raise hand. So how would I solve this problem? Okay, so there is an answer in the chat, which is how would we choose one of the features, right? Like so in some sense, the solution is to filter out the redundant features. Okay, now that is the first issue. Okay, the solution is to like deal with the redundancy by filtering the redundant features. Now there is also another issue that we would normally face, which is rank deficiencies can also occur when the number of input features P exceeds the number of training cases. Yeah, so this is another common problem. Like we would often have lots of features and very few training examples. So now again we have the rank deficiency. So how can I solve this problem? Can we please have someone raise hand and answer instead of typing in chat? Well, you could also type in chat. So how do I deal with this problem? Okay, so there is an answer in the chat, which is to reduce the number of features. Okay. Okay. Also, okay, that brings me to another quick reminder. If you have already read the notes, then you know answers to all the questions that I am asking. So let people who did not read the notes to answer the questions. Reduce the number of features. Or we could also add regularization. So how is regularization going to help us with rank deficiencies, right? Like so, like we saw regularization will help us with overfitting, but how will regularization help us to add, like deal with rank deficiencies? We will discuss more about this in the next lecture. So we will show how this is going to help us with the rank deficiency. Okay, so before we conclude, like I just want to make one note, which is we have been talking about linear regression or nonlinear regression, but with just one output variable, right? But sometimes you might need to predict multiple output variables, or the output is a vector. Okay, so instead of y being r, y could also be r power k, right? Now, how do I modify my linear regression model? So the simplest solution is to use different set of basis functions for each component of y. Or in other words, if I have 5 outputs to predict, I'm going to have 5 set of basis functions and solve them separately. So in some sense, this is doing independent regression problems. Okay, as one could imagine, this is not an efficient way of solving this, like because we are going, when you have k outputs, then you're going to do k matrix inversions, right? So there's actually a better solution for this, which is what we will normally follow, and which is what we will also use in the assignment, which is to use the same set of basis functions to model all the components of the target vector. Okay, so how am I going to do that? So given y hat, like we're interested in predicting the y hat, sorry, of x given w, right? So what we are going to do is we're going to take the x and do the usual basis function, phi of x, just one set of basis functions, okay? Now, usually we will have a w vector, which will be multiplied with this phi of x to get the scalar, right? Instead of that, we are going to have a w matrix so that we get a vector out of it instead of a scalar. So w is a m cross k matrix. Okay, so now remember that, okay, so let's do the simple thing that we always do. So w is m cross k. So when I do transpose, it becomes k cross m, right? Now this is m cross 1. So when you put these things together, you get a k cross 1. So you get all the k outputs by just one operation, which is w transpose p of x, okay? Now the solution w star is exactly the same least square solution, phi transpose, phi inverse, phi transpose y, okay? But the only difference is the y, instead of being a vector, it's going to be a matrix. It's going to be an n cross k target matrix, okay? In some sense, for individual target variables, wk is equivalent to phi transpose phi inverse phi transpose yk. So if you just consider one variable, kth variable, this is the solution. But if you want to consider the entire matrix, then it becomes phi transpose phi inverse phi transpose y. Okay, so what we see here is the solution to the regression problem actually decouples for different targets. However, the advantage here is we compute a single pseudo inverse matrix. Which is shared by all the W's. So this is how we will extend the regression where like you're just predicting one input to k inputs. So we will stop here. A quick note before we leave. Okay, first of all, like I have my office hours now, so I will stay in the call for the next 1 hour. But feel free to leave if you don't have any questions. Second of all, I'm sorry for the delay in the release of the assignments. Like I will definitely release it tonight. And there will be parts of the assignments which you can answer only after the Thursday's lecture. So, but you can get started with your assignments today. But there are some parts of the assignment which will be answered, which you can answer only after Thursday's lecture, which is just in a couple of days. Okay, so I'm going to stop the recording now and then take questions in my office hours. So just give me a minute.